Okay, in this video we're going to discuss how you can draw the graph of a function f if you're given the graph of f prime. And the key tool here is this pair of boxes right here. So we'll start with the first box. F is increasing on an interval, and I want to stress that we're talking about an entire interval. Okay? If the derivative of f is positive for all x in that interval, and that makes perfect sense. If the derivative is supposed to represent the slope of the best linear approximation, the tangent line to the graph, then if the slope is positive, then obviously the linear function itself, the linear approximation is increasing. As we go right, it's going up. And you can kind of tell that at least nearby the function itself, so I guess there's the graph of f, and then this would be the graph of the best linear approximation that passes through this point. If this is positive and increasing, then kind of f has to follow suit. So, I mean, there is some question of how good of an approximation is it outside of some small neighborhood. It might not be a very good approximation. As you can see, the way I've drawn the graph f, it's only increasing for a little while and then it starts decreasing. But the point is that if it's happening on an entire interval, if f is increasing on a whole interval, or f prime is positive on a whole interval, then we can say that f is increasing on that entire interval. So vice versa. So these two are equivalent. And similarly, if it's decreasing, then you would imagine that its slope of a tangent line should also be negative for all values. Okay, so we're going to keep this in mind. But before we do use that to figure out how to draw the graph of f, let's also talk about the double derivatives and how they come into play. So remember, concavity, I mean, listen, what does it mean for f to be increasing? Because that's one of the things we've been talking about here in this box. Well, it means that it's getting bigger, which means maybe as we move to the right, we're moving up too, so maybe it crosses through those 2 points, let's say. But if you're preparing to actually draw what this graph looks like, should I draw it like this? Or should I maybe draw it like that? See, there's a kind of slight difference there. So that's what we mean when we talk about concavity of a function. So if you just kind of look at the following graph, something like this, then you can imagine like a little, I don't know, I like to imagine a little teacup sitting inside of it. And you can tell that the teacup here is pointing up. And then another teacup fits inside of this curve, except this time around, the teacup's pointing down. And then you can kind of tell it maybe starts changing a little bit here. Maybe we only have a portion of the teacup so far, but still you can tell that it's pointing up. So that's what we mean when we say concave up and concave down. This is what's called concave up, this is what's called concave down. How do you measure that? Well, there's actually a very clever way of doing that. Let's pay attention to what happens if f prime is increasing. So here the relationship is between f increasing and f prime being positive. Now I want to go a step further and say whether f prime is positive or negative, it might be decreasing or increasing. I don't know. But suppose that it's increasing. So if f prime is increasing, what does that look like? Well, let's just suppose that f prime has a negative slope. So f prime is negative, which means that, so let me be very clear. This is what I'm drawing. F prime is negative, and what I've drawn for you is the tangent line to f. Tangent line to f at a certain point. Let's say at this point on the graph. Then at some later point, well, f prime is increasing, right? So it's going to be negative, but it's going to be a slightly less negative number. So what is a slightly less negative slope than that? Well, it becomes more mild, right? It's becoming flatter and flatter. That's the kind of picture that's going to happen. So if we draw that and kind of tell what is it sort of looking like, you can kind of tell the function f, I'll even switch colors here, the function f, if it's following suit, has no choice but to kind of look like that. You can already tell that the teacup has to be pointing up. So f prime increasing corresponds to concave up. Similarly, if f prime were decreasing, maybe it looks something like this, and then the slope is becoming more and more negative, like that, then if the function is going to follow suit, in spite of itself, it has no choice but to be concave down. Right? So there's the idea here that I've summarized in this second box. F is concave up on a given interval if and only if f prime is increasing on that interval. So the concavity of f has something to do with whether f prime is increasing or decreasing. Concave up corresponds to f prime increasing. Similarly, over here, comparing the green and the blue, concave down for the function f corresponds to its derivative decreasing. Okay? But of course, if you combine these two boxes together, for example, f concave up on an interval if and only if f prime is increasing on the interval. But f prime is itself just a function. We could call that function g. And here, we know that for any function, don't get confused just because I'm using the same letter f everywhere. This is true for any function. A function is increasing, call it g, is increasing on an interval, if and only if its derivative, call it g prime, is positive on that interval. So here, in this box in the black here, I wrote it for f, but if it holds for f, it also holds for f prime. F prime is a function too. So f prime is increasing if and only if f prime's derivative is positive. That's what this first rule is saying. So that's what we have here. The derivative of f prime is called f double prime. It's what you get when you take the double derivative. It's positive on an interval, for every value on that interval, implies f prime is increasing. And as we just discussed with those pictures, that means that f would be concave up. And similarly, f concave down corresponds to f prime decreasing, which corresponds to f double prime being negative. So we're going to use these two pieces of information to draw the graph. But before we do, let me just mention one important point here. We talked about f prime being positive and f prime being negative. That corresponds to f increasing or decreasing respectively. But what if f prime is 0? So here, typically, f prime is going to be positive or negative on an entire interval. But f prime is likely to be 0 only at a few sparse points. So that's going to be an important difference. So let's think about it for a second. What does it mean for f prime of a to equal 0 for some point a on the x-axis? Okay, well, it means that if you look at the graph of f, the tangent line has slope 0 because the derivative is the slope of the tangent line. But slope 0 is just a horizontal tangent line. So f prime of a being 0 means that the tangent line to the graph is horizontal. There are 4 possible pictures for this that I've drawn here. You have this max, and you can kind of tell that, yeah, the tangent line should be flat there, should be horizontal. And the same thing happens here. And here, if you're kind of keeping track of what the slopes are doing, they're horizontal right there at that red point, and then they're not horizontal any other time. And similarly here, as we get to this red point, it is horizontal. I didn't draw it terribly well, but let's pretend that it is horizontal. So these are the 4 kinds of pictures. And you'll notice that here, to the left of this point, so this red point here, that would be our a comma f of a, right? And f prime of a would be 0. So a would be whatever, if there's the x-axis, a would be that point on the x-axis. So notice to the left of a, the function f is increasing, it's getting bigger, which, as we said before, corresponds to its derivative being positive. And similarly, on the right, it's decreasing, and f prime is negative. And you'll notice that if we're kind of increasing, and then we flatten out, and then we start decreasing, again, in spite of everything, we're forced into this picture. So that's one way of telling that you have a maximum point. You have this little maximum hump right there at that red point. If f is increasing to the left, and it's decreasing to the right, and f prime is 0 at that point. Similarly here, f prime being negative to the left means we're decreasing, and that's what this picture shows us. And then we're 0, we're flat, and then f prime becomes positive. We're increasing. And that forces us into a minimum, decreasing, flat, increasing. So that's how you get a minimum point. So before we go on, let's just think about what this would look like in the graph of f prime. If this is the x-coordinate a here, so I've drawn an axis there, let me erase it. If this is the point a on the x-axis, then the graph of f prime should be positive to the left of a, negative to the right of a, and it should actually be 0 at a. So this picture looks something like that. It's positive, and then it crosses the x-axis and it becomes negative. And where it crosses the x-axis is exactly at a. Similarly here, for a minimum point, there's a, we're negative, and then we become positive and we cross 0 at a. So this is what corresponds to a max on the graph of f prime. This is what corresponds to a min on the graph of f prime. But you can also imagine a couple of other things happening. What if we're positive on both the left and right? What if we do hit 0, but then we go back up? Instead of crossing the x-axis, we just kind of bounce off of it and keep going up. And that's the kind of situation that's pictured here. You're increasing on the left, you level out, but then instead of changing course and starting to go down, you continue back and go back up again. And similarly here, if the derivative is negative on both the left and right, you're decreasing, you level out, and then you just keep decreasing, and you're kind of forced into those pictures. So these are kind of the 4 situations that can happen. And what would this correspond to? You're 0 at a, but your f prime is negative on both sides because the function is decreasing on both sides. All right. So those are just the 4 possible pictures. So now, armed with all of this, let's take this example here of a graph of f prime, and let's try to draw what the graph of f should look like. And we're going to follow the following set of steps. The first thing you want to do is you want to identify the places where f prime is 0. Those are going to correspond to either these max points, these min points, or these, I don't even know what to call them, maybe you'll call them inflection points or something. But these places where it kind of has a horizontal slope, but it doesn't really change whether it's increasing or decreasing. But these 4 possible pictures correspond to where the derivative is 0, so let's figure out where those places are. Find places where f prime is 0. And if you're given a graph of f prime, that's easy to do. Look at all the places where it's 0. I see a 0 right there. I see a 0 right there. I see a 0 right there. And I see a 0 right there. No problem. And let's just, I don't know, it's not drawn terribly well. Let's just make it this point right there, just so it's nice and easy on the grid. Now, find the intervals where f prime is positive and where f prime is negative. So let's keep track of that in the following way. So I'm going to switch between red and blue, and we're going to pay attention to whether f prime is positive or negative here. Alright, so notice that from here to here, it's positive, right? So I'm going to draw that down here. F prime is positive. What does positive mean? Positive just means you're above the x-axis. Negative just means you're below the x-axis. This should be real easy for us. Alright, so you're positive here. Where else are we positive? Well, we're negative for a while, as you can see, and then we become positive the rest of the way from here. So here, all the way to here, we're positive again. Let me switch over to red. Okay, between those 2 points, we're negative. So on this interval, f prime is negative. Alright, so now we've circled the places where f prime is exactly 0, those zeros, and we've circled the places where it's positive and where it's negative. I mean, we've highlighted the places. And that's what I like to do. I like to just draw another line, a horizontal line, parallel to the x-axis, but kind of down a little, out of the way a little bit. And I like to, I guess if you're using pencil on paper, you can't really change colors, but at least mark these things off, and then determine whether these subintervals are positive or negative. So you kind of break it up in this way. So we find the intervals where f prime is positive and where f prime is negative. And remember, the reason we're interested in that is because that's where it's positive, that's where f is going to be increasing. So we should remember to draw it increasing. And where it's negative, that's where f is going to be decreasing. Okay? Now, the next step is you find the intervals where f prime is increasing and decreasing, and not where it's positive and negative, but where it's increasing or decreasing, or aka where the double derivative would be positive and negative. But here we have a graph of f prime, so instead of thinking directly in terms of the second derivative, you should just be focusing on f prime. So remember, if you want to find out information about the concavity of f, you can either figure out is f prime increasing or decreasing, or maybe you'll have some information about the double derivative. For us, we have a graph of f prime, so this is a more useful piece of information than this. Alright, so where is f prime increasing and decreasing? Let's pick two different functions, two different colors, sorry. Let's say gray and green. Okay, and since I did this one on the bottom, the f prime, let's do f double prime on top. Okay, so remember, f double prime, we want to determine if it's positive or negative, and that's just a fancy way of saying is f prime increasing or is f double prime decreasing. Alright, so I noticed that from here to here, f double prime is positive. F prime itself, the function itself whose graph we're looking at, is increasing. So I'm going to draw that interval here in gray. That's where f double prime is positive. Or in other words, where f prime is increasing. Where else are we increasing? Well, I notice from here to here we're increasing. So we're also increasing here. Then we decrease a while, and then from here to here, we're increasing. And then, oh wait, sorry. Actually, we're increasing all the way up to here. So I should have gone 3 squares over. We're increasing all the way up to here. And then we decrease for a little bit, and then we increase from here to here. So those are all the places where f double prime is positive because f prime is increasing. And in green, I'll fill in the places where f prime is decreasing, where f double prime is negative. So it's in green here, and I'll put some notches here so it's easier to tell. Okay, that's where f double prime is negative, negative, and negative. Alright, so remember that. So on these blue regions, let's think carefully about what these things mean in terms of f. In terms of the graph f. We have the graph f prime. What does it mean in terms of f? And I'll switch to black here. Anywhere you have these gray intervals, here for example, here, here, and here, that's where f is concave up. So when you're drawing it, you want to draw it concave up. On these green intervals, that's where you want to draw f concave down. So you know everywhere to draw it concave up and concave down. Now, concave up doesn't mean you're increasing. It means you either look like this if you're increasing, or you can look like this if you're decreasing. Concave down means that you look like this if you're increasing, and you look like this if you're decreasing. So you can be increasing or decreasing. Concavity has nothing to do with whether you're increasing or decreasing. In order to figure that out, you got to look at the sign of f prime. You got to tell, is f prime positive or negative? And that's what these intervals are for. These blue intervals here are where f is getting bigger. It's increasing. And this one big red interval is where f should be drawn decreasing. Alright? So one of the things I like to do to make sure that I kind of capture all of the major places where there's a shift, I like to do step 4 here. I like to draw dotted vertical lines anywhere f prime is 0 or f double prime is 0, because that's where f prime tends to shift from increasing to decreasing. So in other words, I'm just looking at the boundaries between these blue and red intervals on the bottom and also these gray and green intervals. And I just draw a vertical line wherever I see any kind of shift. Here I see a gray to green shift, so I'm going to draw a vertical line. Here I see a blue to red shift. I'm going to draw a vertical line. Here I see a green to gray shift. I'm going to draw a vertical line. Alright, here I see another gray to green shift. There's a shift in concavity. Okay, here the axis itself is already there, so I'll just leave it, but that's where I see a green to gray shift. Then where else do I see a shift? Here, I see a shift from red to blue. Here, I see a gray to green shift, and then a green to gray shift. So notice these intervals really chop up my x-axis into lots of different subintervals. How many? 1, 2, 3, 4, 5, 6, 7, 8, and 9, unless I made an error counting. 9 subintervals. I'm looking at both shifts in the sign of f double prime and shifts in the sign of f prime. Some of these vertical lines correspond to a change in concavity. Some of these vertical lines correspond to a change from increasing to decreasing. We need to pay attention to both of these things if we're going to draw an accurate picture of what f looks like. So once you've drawn those vertical lines, the intervals between them are intervals where f will be either increasing and concave up, so that the graph should look something like this. And what would that correspond to in terms of colors? Well, you're increasing if you're blue, and you're concave up if you're gray. So these would be my gray slash blues. Okay, otherwise maybe you're increasing but you're concave down. Those would be my green blues. Or maybe you're decreasing it and you're concave up, which would look like that. That's my gray reds. And finally my green reds, where you're decreasing and concave down, and your graph should look something like this. Now we finally have all the pieces in place. We're going to finally draw what the graph of f should look like. But I want to be clear about something. If I draw for you 2 graphs of f prime, of f, something like this and something like this, in other words, I just vertically shifted one down. You'll notice that at any given x value, they have exactly the same slope of a tangent line at every point. What we're noticing is a kind of vertical shift ambiguity that exists when you're graphing f. And the reason is very simple. If you have a function f of x and you shift it up, that has the effect of just, if you're shifting it up or down by c, you're just adding some constant. What happens when you take the derivative? If you guys are familiar a little bit with taking derivatives, you'll know that the constant just disappears, and that's the same as f prime. So there's this vertical shift, and it's obvious pictorially too. Pick any point here and draw the tangent line, and it's going to look exactly the same as here. They're going to have the same slope. So you really don't know where to start the graph. So just kind of start it anywhere unless they tell you where to start it. So for me, I'm going to switch to a weird color. Let's pick a vivid color here. Let's go orange. And we're going to draw a graph of f, and I'm just going to start here. Let's just say that at this point it happens to be 0. Okay. Now at first, this first tiny little subinterval here, I'm gray and I'm blue. And remember, gray and blue means I'm concave up and I'm increasing. So I'm gonna draw it looking like this. And I can't be precise about what values it actually takes necessarily. But I do know that once I hit here, I shift from concave up to concave down. So here I've hit this vertical line, and now I've shifted to green, which means I'm concave down. But I'm still in the blue, so I'm still increasing. So now it's more of just like this, right? And then what happens is, I'm 0 here, which means I want to flatten out my drawing here. Now notice that here I hit another wall and I'm shifting from blue to red. That means I'm going from increasing to decreasing, so I had better start decreasing. Do I want to draw myself concave up or concave down? Well, I'm still concave down because I'm still in the green. So I'm going to draw it concave down like this. Alright, then I hit another wall here. And what is this wall? It's a green to gray shift. I'm still decreasing because I'm still in the red. In fact, I'm going to be in the red for a while. I'm going to be going down on this graph. I'm going to be decreasing in this graph for quite a while. But I am going to have several shifts in concavity along the way. So I've been concave down. I better start drawing things in a concave up way. right? And then I kind of flatten out here, don't I? Because that's where I hit another 0. And then I switch concavity from concave up, as I have been drawing it here, to concave down again. But do I draw it increasing or decreasing? Well, no, I'm still decreasing. Remember, we're still in the red for a while. So I'm just going to have one of those weird points over here, right? So what did I just experience here? I just experienced one of these types of situations where I'm decreasing, I flatten out, but I continue decreasing. It's okay, keep going. What does the picture continue to look like? So here, I'm running out of space down here, but let's try and just keep going with it. I have another shift in concavity from green to gray, so I want to go back to concave up. Okay, so you're just going to want to start drawing it a little more concave up looking. And then I kind of reach a peak exactly at this point because we have another 0. Okay, and now we shift from red to blue when we hit this new wall, this new vertical line. And blue means we're starting to increase. We're still gray, so we're still concave up, but now we're increasing. Then I hit this wall. We're still increasing. In fact, for the rest of the way, we're going to be increasing because we're always going to be in the blue. But now I've shifted from concave up to concave down a little bit, right? So now I'm going to draw it still increasing, but concave down. And then I'm going to get flat here because that's where we have another 0. But I'm still increasing. I'm just shifting to concave up. So I'm increasing, but I shift to concave up. So that's where we just experienced one of these guys, where you're increasing everywhere, but you just have a point of flatness along the way. So here's where I have a point of flatness, here's where I have a point of flatness, here's where I have a point of flatness, and here's where I have a point of flatness. And that's roughly what the sketch of f should look like given the sketch of f prime. So you just follow these steps. Find where f prime is 0, intervals where it's positive and negative. Here you know it's flat. Here you'll know that it shifts and so on. Also find where f prime is increasing or decreasing, and especially pay attention to shifts. And then draw the vertical line so you can actually see the walls, so you know that you have to change something every time you hit a wall. And then the only question is, am I shifting the sign of f prime, which means I got to stop drawing things decreasing and start drawing them increasing, or vice versa? Or did I hit a wall where f double prime shifts sign, in which case I've just got to slightly change kind of the way I'm drawing it. Instead of drawing something concave up, maybe I should start drawing things concave down. So that's how that works.